All right, good morning, everybody. Okay, so now outline something on physics 142. Okay, so the atomic physics. All right, so the first thing I want to talk about in this aspect of physics is the contribution of different scientists to atomic structure. So we have John Dalton, that is the first atomic theory. We have John Dalton atomic theory, right? We have the J.J. Thomson's experiment, J.J. Thomson's. We have the Ernest Rutherford experiment, Ernest Rutherford, and we have the last person to be Neil Bohr. All right. So if you move from Neil Bohr, you have Ewing's Schrödinger equation, Ewing's Schrödinger equation. That is the contribution to the hydrogen atom. So these are the the four basic theorems, or the five basic theorems you need to consider if you are talking about the concept of atomic physics. So these are the scientists that contributed to the study of atomic structure. So basically, if you want to find the different scientists, their theorems, and how to go about the things they derive. Now, it is very easy. So we start from the first person called John Dalton. So from the John Dalton's atomic theory, what is John Dalton talking about? So there are five theorems in John Dalton atomic theory. The first one is that John Dalton says that atom is defined as the smallest indivisible particle of an element. All right. So and it was modified. All right, that the discovery of subatomic particles like proton, neutron, and electron has countered that postulation. So that's the first. He said that atom is defined as the smallest indivisible particle of an element. So it has been modified that theory is not generally correct any longer. That the discovery of subatomic particles like proton, neutron, and electron has countered the postulation. So the second thing John Dalton said, right, is that John Dalton says that atoms can neither be created nor destroyed. I said that there are five theorems there. So it's an atom can neither be created nor destroyed. Now, is that theorem longer true? No, because the discovery of nuclear reactions, all right, what we have are nuclear fusion, all right, and nuclear fission. We have nuclear fusion and nuclear fission. It has actually countered the postulation that atoms can neither be created nor destroyed, because with nuclear fusion, in nuclear reaction, it is a process whereby two or more lighter nuclei combines together to form a heavy nucleus. All right, so that suggests that atom has been created through nuclear fusion. Now, why nuclear fission is the breaking down, all right, of a heavy nucleus to obtain two or more lighter nuclei. So those two suggestions have actually proven to us that the theorem from John Dalton that atom can neither be created nor destroyed has been countered, all right, it has been modified, all right, the discovery of nuclear reaction where we have a nuclear fusion for creating atom and nuclear fission for breaking down or destroying atom. So that's the second. Then number three, all right, of John Dalton's experiment, John Dalton says that atoms, right, of the same element look alike in all aspects, right? That is the top postulation of John Dalton's theory. Atoms of the same element look alike in all aspects. So is that still true? No. Now it has been modified because the discovery, all right, of isotopes has actually countered that postulation. All right. What are isotopes? Isotopes are elements that have the same atomic number or proton number, the same proton number or atomic number, but different mass number. So there's equivalence in atomic number, but there are differences in the mass number. So atomic number is called the proton number, while mass number is called the sum of the proton and the neutron number of the element. For instance, we can have chlorine. Chlorine has a proton number of 17 or atomic number of 17. Like I said, atomic number is also called proton number. Then we have 35 as the mass number. That is the proton and the neutron number. We have another chlorine to be 17, and we can have 37.5. This existence of the same element, all right, with different same proton or atomic number but different mass number is what we call isotopes. All right, so it has actually countered the postulation from that John Dalton that atoms of the same element look alike in all aspects. No, because these are the same but they are different in mass number. That's theorem or postulation number three. Then postulation number four. All right, now John Dalton also said that that atoms of different elements do not look alike in all aspects. Atoms of different elements do not look alike in all aspects. So is that still true? No, because there are discoveries of some elements that can have the same different elements, but they have the same atomic number. All right, or different elements with the same mass number. All right, so we can say that the existence or the discovery of isobars and isotopes has actually countered the postulation that atoms of the what of different elements do not look alike in what all aspects. So you can find what isobars are. So there are elements that are different, but they have the same mass number. There are also elements that are different, but they have the same atomic number. Of course, yes, we have the allotropes of what is it called? Of I think hydrogen. Now we have three there. We have protein, we have tritium, and we have deuterium, called the heavy hydrogen, 2H1 and 3H1. All right. So now, the discovery of isobars and isotopes has countered the postulation that atoms of different elements do not look alike in all aspects. Then, theory number 5 now. Number 5 now says that atoms combine in smallest whole number ratio. Atoms combine in smallest whole number ratio. Is that still true? No, it has been modified because when you check things like carbohydrate, protein, polymers, all right, now they are gigantic molecules, all right. So atoms of the same element or atoms combined in smallest whole number ratio rather, all right, is the fifth theorem of John Dalton. And the modification is that the discovery of gigantic molecules like carbohydrate, proteins, and polymers has countered the postulation that atoms combine in smallest whole number ratio. Because when you check some of those things, or some of those compounds, you find out that one carbon can be having 17 atoms, all right, C17, we have A22, we have O, whatever, all right. So for discovery of polymers, of protein, of carbohydrate has countered the postulation that atoms combine in smallest whole number ratio. So all of this concept is all right, the John Dalton's atomic concept. All right. So like I said, there are 5 different scientists. So this is just for John Dalton. So I've stated the 5 and I've stated their modifications. So this is the first thing to know about John Dalton. So the next person we are going to be looking at is called J.J. Thomson. So what was J.J. Thomson experiment trying to talk about? Okay, once you have seen John Dalton, that for the first, John Dalton said that atom is the smallest individual particle of an element. For the second, he says that atom can neither be created nor destroyed. For the third, he says atom of the same element look alike in all aspects. For the fourth, he said atoms of different elements do not look alike in all aspects. And for the fifth, he said atom combined in smallest whole number ratio. So what was J.J. Thomson talking about? So that's the second scientist. This scientist number 2. The first one is the first theorem was that the first scientist. This scientist number 2. So let's look at what J.J. Thomson was talking about. Now, for J.J. Thomson's experiment, now J.J. Thomson did 2 things. All right, there are 2 things that J.J. Thomson did. All right, the first thing, all right, J.J. Thomson did is that he discovered. All right, J.J. Thomson was the person that invented the discovery of charge to mass of an electron charge to mass of an electron. This is the person that invented it, of an electron. And the second theorem, like I said, there are 2. He discovered is the discovery of cathode ray tube. So I will do the 2 theorems, all right, quickly, and we'll call it a day for this aspect of video. So now, what are we talking about when you talk about charge to mass of an electron? What are we talking about when you talk about cathode ray tube? Now, when you talk about the charge to mass of an electron, all right, so let's observe something. Now, there are 3 forces we are going to be using, okay, because the idea of charge to mass of an electron is actually talking about the concept of an electron, all right, moving. Of course, we know that electron is the negatively charged, all right, in your electrolyte, of course. So now, if you are considering an electron now, let's say you have an electron here, because when you get to Rutherford's experiment, I'll draw a diagram, then you'll find, of course, nucleus is in the center, it's at the center. Now, an electron revolves around the nucleus. So what of if electron is entering? So that is the first theorem. When an electron, the first one is electron entering into an electromagnetic field. So this is the first thing we have in charge to mass of an electron. Okay, so if an electron enters into an electromagnetic field, what is going to happen. So what's going to happen is that now, of course, we know that in magnets, the force in the magnet is Fb, which is what? BIL, all right? Magnetic force is either BIL, all right, sin theta, or BQV, all right? F is equal to BQV. These are the two forces of magnet. We can also use F, force of magnet is equal to BIL sin theta, or BQV. Fb is equal to BQV sin theta. So those are the two magnetic forces we have, all right? They are not more than two. Okay, for this now, okay, what do we have? So we are saying that electron is entering into an electromagnetic field. So now what's going to happen is that there's going to be deflection. All right, what is deflection? Deflection is actually the change in direction of electron when it passes, or changing the speed of the electron when it passes from one medium to another medium. All right, changing the speed of an electron when it passes from one medium to another medium. So if electron enters into an electromagnetic field, this is an electron so entering into what we call an electromagnetic field. Okay, electromagnetic field. So what's going to happen is that there's going to be deflection. So by the time this electron enters into the field, all right, they will be changing the speed of the electron. Right, this is the electron. Now, if there is a change in speed, what can we do for deflection not to occur? For deflection not to occur, the force by which this electron is moving is what we call an electric force, Fe. While the force here is what we call what? A magnetic force. So in order for deflection to happen, your Fe is going to be not equal to what? F is not equal to Fb. If deflection is going to happen, if an electron is entering into an electromagnetic field, all right, and your Fe is not equal to Fb, there's going to be deflection. But if your Fe, the force in the electron, is equal to Fb, all right, there is not going to be what? Deflection. So we have two things there. If your electron is entering into the field, all right, if your Fe is not equal to Fb, all right, what's going to happen is that there is not going to be deflection. But if your electric force that the electron is moving with is balanced with the magnetic force, there is deflection, here there's no deflection. All right, so that is that. So let's look at when there is no deflection. That is when when there is deflection, your Fe is not equal to Fb. But when there is no deflection, your Fe is equal to what? Fb. Now this is electric force, while this one is magnetic force. So what's electric force? Electric force is given as EQ. All right. How do I know it's EQ? Electric field intensity is what? Force per unit charge. All right. So I have E is equal to F over Q. So I'll make F is equal to formula this over 1. So what do I have? This go with this. Then I have what? EQ is equal to what? F, or F is equal to what? EQ. So that means electric force is the product of electric field intensity and the what? And the charge. So anywhere I see the electric force that the electron is moving with, I write it as what? EQ is equal to what? FB. Now don't forget that I said that your FB is BQV, all right, sin theta, but there's no angle subtended. So if your FB is equal to BQV, all right, anywhere I see FB, I write as BQV. So I have EQ is equal to BQV. Now, but our Q is the charge here, the electronic charge, and the electronic charge is equal to E, all right. Q is equal to E. So anywhere you switch, you write as E. Okay, now, but before we do that, what is your E? All right, your E, which is electric intensity, is voltage over distance apart according to parallel plate capacitor. So if this EQ is equal to BQV, so and my Q is equal to E, so I have EE is equal to BE, then the velocity. All right, now of course my total force is equal to what? Mg. So everything is equal to what? F. All right, and F is equal to mg. So I have EE is equal to BEV is equal to mg. Okay, so if that is the case, what did I say E is? Electric intensity is equal to what? Voltage over distance apart. So I have V over D, then all into E is equal to BEV is equal to what? Is equal to mg. All right, so once my BEV, which is what? Magnetic force, is equal to what? The force, all right, normal force in physics, which is mg. Then I can now write V over D all into E is equal to mg. All right, so V over D is equal to mg. Then I'm looking for charge to mass, this charge and this mass. So what's going to be the ratio of E and M? So I'll move D to the other side. So if I move D, I have V over D all into E is equal to mg, D over 1. Alright, so D is going, I have V is equal to what? Mgd. Don't forget I'm looking for what? For the charge to mass of the electron. That is